second to okay, so our speaker today is Jeff Bassel. Jeff was an undergrad at Colorado School of Mines, and then on to the Courant Institute at NYU. He's doing a master's in applied math. And then he got his PhD from Colorado. He was a student of Nick Brummel's, and I guess quasi was your doing, but I think was his primary advisor. And he liked Boulder enough that he has stuck around since then. Postdoc. He works on a variety of topics in fluid mechanics, has done both analytical and simulation work, and today he's going to tell us about the sun.
Yeah, thank you. Yeah, so this first slide, I put this up there for a reason. So this object is actually the Aztec sunstone. And a lot of people mistakenly call it the Aztec calendar, but it's actually not a calendar. But I actually like it as an analogy for the kind of problem that I think that the solar interior is. If you're stumbling through the jungle and you find this thing and you don't know anything, you see there's certain regularity to it, but wow, it's confusing. There's lots of things going on here. And if you were to just stumble across and look at the sun and see sunspots and these kind of things that you see on the surface, it might look a lot like this. Fortunately, we know some physics, and if you know something else about Aztec culture, that you could sort of use as your physics, and you can sort of see there's regularity here. There's 4 things going on here, and you might attribute that to the 4 centuries of 52-year centuries of Aztec in the Aztec calendar, with the 5th era there sitting right there that's coming up, and it's. There's the days of the Aztec calendar going around there that you may be able to recognize, and then you can start to fill in sort of details. But in the end, you sort of have this overarching feeling that somebody is sticking their tongue out at you throughout the whole process. And so that's sort of my little analogy. But to jump into the sun, okay. So what does it look like? Where do we start? This is an image in ultraviolet from the SOHO spacecraft. Of the sun, and you can see that there's obviously some features that jump out, just like on the sunstone. There are these patches of bright spots that are lit up in UV. People who know something about physics automatically associate those with magnetism, although it's not 100% foregone conclusion. But it turns out that's a pretty good guess. There's this fuzzy stuff going on up here. There's some dark bits. These arching lines here and this kind of stuff. And okay, so the sun rotates. This is a movie. And you can watch this thing go around. These things kind of, flare up a little bit, get brighter and darker. And sort of, in my view, one of the, biggest questions in all of science is, why are these things here? Why are these bright spots? Why does the sun look this way? What creates this? And these, in fact, are, very highly related to magnetism. And so, where does this magnetism come from? And as you can see here, this was taken when the sun was active in 1999, and we are counting down to the new millennium here, 27, 28. Now, hopefully everything goes well when we hit 2000. Well, when the clock changes over in the year. So, it stopped. So I guess it didn't work. So anyway, so that's sort of the gist. All right, so when you see this, you say, okay, well, what do? We start looking for patterns. And there are actually some really intriguingly regular patterns that kind of jump out that you can start of getting a handle on. The first is if you look at magnetism. So this is a synoptic map of magnetic fields as measured by Zeeman splitting. And you can look at this thing. This is taken, I don't know, at some point in the past when the sun was a relatively active phase. And you can see that there's some nice things about this. So the magnetism exists in these 2 nice sort of stripes, more or less, that are at any given time at some particular latitude. The magnetism tends to be ordered in these spots with the colors denote polarity. And in the northern hemisphere, you have at this particular time you have yellow leading purple, and in the southern hemisphere you have purple leading yellow. And so it's not always perfect. Like there are some areas where it gets a little bit unclear as to what's exactly going on. But for the most part, there's this well-ordered pattern. And of course, like any good synoptic map, you can show it in time as well. And the first thing we do is we'll rotate around and see what this thing looks like at any given time in space, or any given time. And then it unrolls. And you see the nice two bands there, and the equator is in the middle. And what this thing's going to do is you'll see this thing, you'll see as time progresses down here, the spots go away. All right? And then they're going to come back again. And I'm actually going to stop it when they do. And now you see that they've done something else. Now in this case, before we had yellow leading purple, now we have purple leading yellow. So the polarity of these things is reversed. So there's another thing to get a handle on. And another aspect of this also is that there's a certain tilt. And actually, I should have shown it in the previous one. But there's a good example. A lot of times there's a somewhat systematic tilt where the leading one is kind of pointing towards the equator, and the trailing one is kind of pointing towards the pole. And these things progress this way. So there's certainly something there that is somewhat simple. And you can see also they migrate towards the equator as well, disappear, and then they will eventually begin to come back again in the same polarity as they started. So that was a full cycle, more or less. Yellow leading purple. All right. So there, you see this pattern, and you try to come up with a model for it. But before we start thinking about models, this is sort of a nice way to quantify it. This is a famous butterfly diagram. And this shows that sort of, what you might have seen is that migration of sunspot activity from higher latitudes to the poles. At any given time, at some point in time, you get sunspot emergence at some latitude around 30 degrees north and south. And then over time, that emergence happens closer and closer to the equator. And eventually, the opposite polarity patterns will somehow annihilate each other, and then the thing begins again. And so this forms this nice butterfly diagram. And this may be quite familiar. A little less familiar is the torsional oscillations, which is this pattern of velocity, speed up and slow down. So the sun rotates, and as we'll see in a minute, well, it rotates and it differentially rotates as well. So there's a certain large coherent time average signature of the rotation. But there's also this time-dependent rotation where, and this has been observed for a long time at the surface, where you get these bands of relative high velocity and relative low velocity that propagate along in somewhat of a butterfly pattern as well. So in one sense, if you can figure out either one of these, you imagine you must be able to figure out the other, or at least any theory that explains one better have something to do with the other in some way, because they obviously are, linked in some sense. Okay, so a little bit of structure of the sun. I'm assuming that not everybody knows about stellar interiors, but so we have the sun. It's roughly a radius of about 700 megameters, a megameter being 1,000,000 meters. Is a nice fiducial unit to use for these. And outer 30% of this is convecting. And then the inner 70% is this radiative zone where energy that's created in the core, and your core leaks out very slowly over long periods of time. And eventually the opacities become too thick, and it can't radiate out anymore, and you get convection. And there are all these different scales of convection. The smallest scale we call granules. These are about a megameter, 1 megameter or so. And this is a nice movie with the Swedish telescope in La Palma that shows this nice convection, this boiling, very turbulent convection going on near a sunspot. So this is sort of the smallest scale of motion that we observe, clearly distinct small scale of motion that we observe on the surface. And then there's also a network of these tiny granules that form, what are we call supergranules. And in between there's these mesogranules, but they're not quite as clear. But there is certainly the supergranular network, and this shows a sort of a velocity, horizontal velocity pattern in the vicinity of an active magnetic region. So if you look here, sort of a sunspot is there, and then sort of this larger patch would be an active region. This is a relatively large active region. And there's this larger, scale of convection as well. And then we've never exactly observed it at the surface, but we have good reason to believe that there's actually even larger scales of convection that exist below the surface, which sort of dominate the convection zone in a lot of ways, but don't penetrate their way through the surface very well. And those probably have a lot to do with what goes on inside. So this is just sort of an overview of the various scales in the structure. Now, what about what goes on inside more? So we know about flows on the surface, but it turns out with helioseismology. So you can, the sun has these overtones. It rings like a bell in a lot of ways. There's acoustic waves that are trapped, within this, and they're to a very high degree linear. They're generated by those small scales of motion at the surface, most likely, and they have a bunch of overtones. And you can calculate the theoretical frequencies, and then you can also measure an actual frequency spectrum of in Doppler at the surface, and you can get a difference between the expected and the measured frequency, and based on that, you can back out the frequency splittings that would be they'd be due to things like rotation, local rotation, splitting frequencies, and also adjustments as, from the stratification. So when you do that, you get this lovely picture of the interior angular velocity. So you have, it's been known for quite a long time that there's, observed at the surface that you have a fast equator and a slow pole. Red is fast, blue is slow. The equator goes around in about 25, 26 days or so, whereas the pole takes about 31 days to go around, something like that. And there's this nice gradient, latitudinal gradient going from north to south, south to north. But inside, there was this surprise that nobody really expected. And that is that if you go down deep enough, there's the interior, the radiative zone, is rotating as if it was more or less made out of rock rather than fluid. It's rotating as a solid body. To within the error bars on this is rotating as a solid body. You see some structure, but who knows about it. And then in the interior, in the convection zone, in the interior of the convection zone, the surface pattern more or less imprints its way down into the interior in a constant way. So this is more or less constant contours on radii that exist throughout a lot of the mid-latitudes. And then eventually the problem with it is that something's got to give. You have this solid body rotating interior, and you have this differentially rotating convection zone. And the transition between these two things forms this fascinating boundary layer, internal boundary layer, if you like, that's correctly titled the tachocline, as a change in rotation. So this tachocline region is something I will discuss quite a bit. And this is, when you look at this image, you say, something's going on at the surface. And if there's something inside here that's doing it, the first thing you might think, the smoking gun, might be this interesting boundary layer that's here. There's also another very interesting boundary layer that has been much less studied and was debatable about if its even presence was somewhat debatable up until quite recently. It's the near surface shear layers, and they're a bit harder to see with the eye. But you can see that as you go along a constant contour of radii, and as you go up to the surface, you get this sharp decrease in the rotation velocity, whereas throughout most of the convection zone, the rotation is actually increasing as you go inward, except for the poles. So at low latitudes, it's actually decreasing as you go inwards. All right, so that's sort of what we know about it. All right, now we need to work about a model. All right, so we set out, and this is a sort of somewhat of a famous picture in solar interior community. This was drawn sort of in 5 minutes or so by my former PhD advisor, Nick Brummel, and this has been being passed around the community for probably a decade now. And and everybody uses it to describe the sort of the standard picture of the solar dynamo and what we think is going on. So, okay, we have emergence at the surface. So there we go. That's ultimately the goal. And we have a tachocline. We have some shear going on here. We have a radiative zone, we have a tachocline, there's a convection zone, and there's a photosphere. And there's all these things going on. This is kind of complicated. The numbers start here with 0, with some sort of maybe perhaps a local dynamo going on or whatever, but I won't discuss this too much. But you somehow, through some process, unknown perhaps, you get magnetic field that pervades this tachocline, this shear region, to some degree. And through just straight up induction from the magnetic induction, you can imagine some weak field that threads through this will get stretched out and elongated in the longitudinal direction, in the toroidal direction, wrapping around, which can produce strong and perhaps concentrated structures that exist in this tachocline. So that's sort of the naive idea, or at least that's one idea. Right? And then by virtue of their energy density, magnetic fields just having energy density, they can supplant some of the gas energy density or gas pressure. So they have magnetic pressure, which can supplant gas pressure in these things. And if these things are in total pressure equilibrium, then you will have somewhat lower gas pressure as a result of the fact that these things have magnetic field involved in them if it's concentrated enough. And given, and depending on the process into which these things are pulled out, if these things are pulled out very slowly in thermal equilibrium, then the temperature will be constant, the pressure, total pressure will be in equilibrium, the gas pressure has to be lower, so the density will have to be lower. If these things are pulled out rather fast so that it's an adiabatic process, both the temperature and the density will change, but nevertheless the density will still lower, and you'll get a relatively low density region that sits in this, and in the presence of a stratification, the things might become buoyant and want to rise under this action of this magnetic buoyancy. So you get this process, sending magnetic structures from this region perhaps into this convection zone, where lots of other things happen. You have rotational effects, you have turbulent convection interacting with these things, and then perhaps these things that rise at the solar surface, and we see them. So this is sort of the this is the picture called the interface dynamo, because there's this interface dividing the region where you're making it and where you're eventually seeing it, and where you're regenerating other field as a seed field. So, all right. So now, what would this guy say about all this? Does anybody know who this is? You don't actually have to be a solar physicist to know who this is, although he isn't tremendously well known. But you don't have to be a solar physicist. Now, who is this guy? And what does he know about modeling complex processes like the sun?
My guess is that's about, it's not that much.
No, it's Rube Goldberg. So Rube Goldberg was an American cartoonist, and he drew these lovely cartoons. He was actually a political cartoonist. He won the Pulitzer Prize for political cartoons and satire. But he had this thing where he drew these lovely machines that bear his name today, these Rube Goldberg devices. And it's one of these things, like you want something simple, like toothpaste. And, well, here, I'll go to the next slide. So you want something simple, like toothpaste. And, you pull a string, and there's an A, and then, there's some action, and then, ball rolls down, and then there's some cards, and eventually the bird, flies away, and then the rock falls, and he gets his toothpaste, right? Now, gosh, it occurred to me at some point that, we're kind of along the same lines here, really, in some ways, right? This has letters, A, B, C. This is numbers, 0, 1, 2, 3, and so on. But, you do have this sort of process that goes around. And, if number 7 here is the toothpaste, then, 0 here might be the, pulling the string. So we have this thing that we know we want to explain. And at this point, we've drawn this thing. And this is not exactly a criticism, but it is saying that, that this is somewhat of a Rube Goldberg machine. Now, that's perfectly fine. There's lots of things that are complex, and that's okay. But the issue is that this was a picture that was drawn conceptually a long time ago, based on I think somewhat naive physics. Just sort of very simple arguments based on very simple problems. The issue is that both machines could work. If I showed you a picture of this and said, "Could this work?" you can't say it won't. But it is much harder to say if it really does work. And if you want to determine that, if it's really important to determine that, there's a couple of ways you could do it. There's the comprehensive approach of just simply building the whole thing, as you see in the diagram, and running it and seeing if it works. Now, it's likely not to work if you do that, because you're likely to have made a mistake somewhere. And the question is then pinpointing where you made that small mistake. So another way of doing it is you could, in fact, dismantle the machine. And you could take the individual parts and see if they work by themselves under some reasonable situation, do an experiment in some sense. You take the bird and you see if it's dead. And if the bird is alive, at least you know that that's a possibility. If it turns out that the bird is dead, you say, well, that's not going to be a component that functions within this system very well. All right, so for some of my past research, that's kind of what I did. I took a section of this, and people have taken smaller sections, and I took somewhat of a bigger chunk and worked on it. So there's this issue of shear. So actually, I'll go back here. So there's this issue of this shear generation. You have some field here. You create some stuff, and then you have this buoyant process. And I did spend some time sort of studying these components of the dynamo machine and seeing if under some reasonable circumstances it can work. And then if it does, exactly how does it work? But here's what we have: is we have this thing we know, or we trust somewhat reasonably, and again, sort of another cartoonish picture that's been going around the community for quite some time is these little drawings here, where you have this process of winding up a magnetic field. You have some poloidal field here, some dipole component, and the shear grabs a bit of this thing and winds it up, and where you get the lines close together is where you have stronger fields. and it has the right orientation, north and south, the right polarities. And then you have some process here which then perhaps regenerates this colloidal field and produces some sort of transport, where you see these little loops through perhaps magnetic buoyancy getting lifted up and transported to the surface. But drawing this picture doesn't prove a thing. It's just a cartoon. And down below we have what I like to say is that this is sort of the toothpaste, right? This is sort of what you really want in the end. And this is a lovely movie by Hinode. We used to have some idea of what sunspots looked like, but a couple of years ago, this was a microscopic view with a very high-resolution camera on the spacecraft that actually observed, what it really looks like when something comes out. So this we call the trilobite movie for a reason that you'll see very shortly. And there's a sunspot that pops out in this rather complex manner, and then you see these trilobites of magnetism that are connected up, and then this one here has some partner where we don't know where it is. This is in the end what we're trying to explain, and there's a large chasm between this kind of a thing and this kind of a result, where this is very fibril, very complex, very structured, and then forms this nice ordered object in the end. Now the question is, can you bridge this chasm, or are we missing something, or what? So, all right. So taking the pieces of the puzzle apart, people have started, a long time ago had done sort of very isolated studies. So the very first one is there was these fellows, Fausto Catania and David Hughes, about in the late 80s, and they studied magnetic buoyancy of a layer where they took a stable stratification, put in a slab of magnetic field by hand, sort of as an initial condition, and let it break apart and rise. And it's more or less like a Rayleigh-Taylor instability. And this is one frame from their work. And this is this used to be one coherent slab that just went across uniformly, and it broke apart, and you form these mushroom-like structures that perhaps these are two-dimensional calculations, by the way. And in this case, the magnetic field comes out of the screen. And this is a slice through, if you like, the meridional direction. So if this would be the radial direction here, this would be the latitudinal direction, and shear would be creating a magnetic field that's coming out at you. And then these things would be rising through some sort of interchanging of the magnetic field lines and forming these tubular-type structures. All right, so this was sort of one success. And then they eventually do these interesting dances, and the thing become quite complex. But nevertheless, it was somewhat of a success. It says you can get magnetic buoyancy, and it can form these tubular structures. However, there was sort of nothing saying how it got there in the first place. It was put in there by an act of Fausto and David. So then there was sort of this idea, this predecessor graduate student before me, Kelly Klein, working with Nick Brummel, this fellow Fausto as well. They decided to try to create self-consistent shear-generated magnetic buoyancy. So they impose a shear through some process which is left unexplained. They impose a background magnetic field. And through that, they create magnetic structures that then can become buoyant and rise. And so there's this movie here where you start off with no magnetism, no strong magnetism, and you have a shear that's being forced in this. And the shear is created such that it will, in fact, induce structures like this. These have opposite polarities. This is magnetic energy. But they're created, they sit there for a while, and then they begin to do this rising dance where they alternate, and this is under the action of buoyancy. So this is sort of a first proof of concept that you can, in fact, make shear-generated magnetic structures. And they do this rising, and they kind of do this little shaking off thing, which is kind of nifty. The only problem with this is that the morphology of these structures is left unexplained. It's created by the shear. The shear has a...
the magnetic field is out of the plane of the screen then?
In this case, the magnetic field is lined with these tubes. So these if...
So there's a very weak...
There's a very weak field going this direction through here. And there's a shear that's coming this direction, which is modulated in the vertical direction, in the up and down direction.
And why are they separate tubes?
Because this is, it's because it was the way it was forced. This is a periodic simulation, and so this is forced with a sort of cosine profile, where you have one bump of the cosine going in one direction and the other one going the opposite direction. So these, again, are opposite polarity tubes, but the magnetic energy looks the same. So anyway, it's a proof of concept, but the morphology is left unexplained. And if we were to look at the solar differential rotation profile and say that the things we observe at the surface have to look like what the shear itself looks like, we would have whole hemispheric sunspots, which we obviously don't have. So there needs to be some process of breaking these things apart if this is what's going on. And this kind of thing is one idea, right? So this breaks it apart. And this, the morphology of these things is determined by the instability, but the magnetism is unexplained. And in this case, the magnetism is created self-consistently, but the morphology is unexplained. And so maybe you can combine these two ideas, and that's what I began to do. So yeah, the problem with layers is they're presupposed and not made through kinetic processes in these cases. And then the tubes is the morphology is imposed by the shear geometry. But instead, maybe we could assume something that actually looks somewhat like a Rachocline's shear, something, a model of it, and and create processes, combine these two ideas. So that's what I did. So I imagined a Cartesian computational domain, and imagine taking this is from the Catania-Hughes work. This is a diagram that's very nice about taking a small section, cutting a section out of this region where the Rachocline might be, taking it out and turning it right side up. And taking this box and forcing a shear flow, where, like in the Rachocline, you have the different, the faster rotating convection zone going one direction at some constant rate, and then you have the slower radiative zone going the opposite direction in this particular frame at some other constant rate. And through this thing, you thread a vertical magnetic field, which will then interact with this Rachocline-like shear junction. Okay, and that's what you do. So you take this thing in a 3D calculation and you force it through some sort of a body forcing. The shear flow, the magnetic field is just in there for some reason, and that's what you get. Is you initially get this one-dimensional dynamics. This thing will shear out a layer that does not depend on the toroidal x direction. It will not depend on the longitudinal y direction. And so it's a initial one-dimensional transient. It forms a layer that's isolated to where the gradients of the shear are. And you see that. You form it, you start off with a horizontal magnetic field that's initially 0, and over time you build up this layer, or this spike, in magnetism. And you get these imbalances that produce these waves, which are somewhat interesting in one way or another. But also it does the honorable thing, and that the density adjusts along with it. So as you're building up this layer, you get a density that was initially a polytrope, just as a local approximation, as a local density contrast, but it builds up this low density region. So this has a potential for buoyancy, and that's what happens. So we ran these calculations. They're somewhat big. They require a lot of time steps. They require decently high resolution. In this calculation here, this is a magnetic energy at some point, a snapshot of magnetic energy. So I have the vertical direction is up and down. I have the longitudinal direction, if you like, toroidal direction this way, which is the direction that the magnetic fields are being induced. And then you have sort of this cross direction, which is, if you like, latitude. And I have a shear that's running, one direction at the top of the box and the opposite direction at the bottom of this box, creating this layer in the middle. So I have a movie here that shows this process. So you have nothing, and at some point a one-dimensional layer is built that's just a slab, and you have these waves that are actually propagating up from this imbalance in this tension-driven process. And then at some point what you'll see a very quick instability that's a nice elongated mushroom-like, noodle-like instability, and then you'll see some more nonlinear dynamics. So there goes the instability right there, and then you get a mess. You get a lot of nonlinear interactions. Obviously the shear flows are carrying bits of magnetism downstream and upstream. You see these arching structures like this one here forming and then dissipating. And you get these rising events. One interesting thing is that the size of the scale of the structures that you pick is actually not even determined so much by the instability scale. If you saw the initial instability, it was quite a fine scale. There was about 10 or 12 of these things across, and later on you're kind of getting 2 of these things in the box. So there's a coarsening effect here, but nevertheless it does what it does, and you can study it. And it forms, sometimes it gets quite cloudy of magnetism here. Very turbulent. You can see that this is a field line rendering looking down from the top of this box. And these things forming these tubular structures that are somewhat isolated, and they're somewhat twisted. They form some twist, which we do see at the solar surface. So okay, so far so good. Perhaps a success. Maybe we're on our way to learning something here. But we need to kind of delve into this a little bit more first. So the first thing, another thing, just to show sort of a la the Catania and Hughes work, you take a layer that's uniform, and eventually this thing through this instability breaks up and forms these mushroom-like structures, which look very similar to what we saw back in the late 80s. And this is a mostly two-dimensional instability. And if you look at the density perturbations, they correlate very well with the magnetic field rising. So green is low density, light stuff. And so they correlate very well. So it seems like we're doing the honorable thing there. All right, flux transport. It is not very efficient. What do I mean? So one thing you can do is you can take that calculation, that 3D calculation that I did, and you can. The thing we're interested in, if you look at the solar surface, if you go back to the second slide I showed with the yellow and purple sunspots, the yellow and purple magnetism. If you take a band of that and you average that thing up going around, you're going to get a coherent magnetic polarity. You're going to get a coherent flux that exists at the surface, some m equals 0 component of that. And what we're sort of interested in is if we're making it down below, how much can you get a flux to the surface? So you can take that simulation and average it over horizontal layers. And you can have that then as a function of depth and time here. And so when you do that, you see that, you form this nice, consistent, persistent, I suppose, central layer of magnetism here, that's localized in depth. And then you have a couple of notable features. So there's this alphanic transient. So you saw these waves propagating up in both the one-dimensional line plots and also in the three-dimensional movie. You form the central layer, and you saw these rising sheets as well. So now these things do a great job of actually flux transport. Now these are transients, but in a dynamo process, you're sort of rebuilding your field every 11 years. And so, if you're starting off with a new field, you're going to get a new Boeing, you would imagine, every 11 years. So I'm mentioning this now because this kind of, you should be suspicious of this. But anyways, this does a great job of flux transport. You take a lot of the green stuff and you move it up. Okay, so that's what it's doing. Now, these other streaks are sort of rising flux emergence. These are buoyancy events, and these buoyancy events don't really do that well of a job. They, you can see something will get started and it'll just kind of peter out, and yellow is where you don't really have anything going on, and so this thing will just peter out into the yellow. And sometimes you get ones that go, a little higher up, but they never really get there. And there is eventually a slow piling up of green stuff near the top. But it really doesn't do a very good job of transporting flux. You don't see like this layer, like moving up in any coherent way.
Is this because of the dynamic expansion of these flux tubes, or?
Well, actually, I'll actually discuss that in just. That's part of the reason, perhaps.
So what's happening below? I mean, if that's
this stuff down here.
Yes, I mean, gravity is down.
Yeah.
So why are these features moving downward?
These guys.
Right, yeah.
Yeah, so these are, actually. So if you'd like, it's sort of a non-linear version of, so you have most of the stuff, like these mushrooms are headed up, but you see these little loops that are going down. There has to be, if you send velocity up, there has to be a return flow. And the velocity that sends stuff up will do a better job on average of moving stuff upward, but there is some weak transport in the downward direction. And once this thing gets going, it sort of becomes intermittent. And
so, above this layer, the fluid is neutrally stable to convection, or
no, this is subadiabatic. So this whole domain is
subadiabatic
all the way up.
But fairly weakly subadiabatic.
Yes, and in fact, actually, I don't mention this in this at this point, but actually, less subadiabatic than you would expect for the tachocline itself, or at least only as much as you would expect, but no more. No, this is fully compressible. So this is fully compressible stratified MHD. I think the whole box is about 2 to 3, whereas this sort of central layer, this is sort of about 1, and I give it a bit of a buffer zone to just kind of see how these things rise. You know, I don't put the layer right at the bottom. I don't want to put it right at the middle either. So, yeah, I believe there's a factor of 10 density contrast across the whole thing, roughly, which is consistent with a you know, a chunk out of the solar interior. There's a bit of a buffer zone because you want to see how things eventually kind of go, and you don't want to interfere with the boundaries. And I don't want to put a convection zone in this right now, just to not to complicate issues. You know, I would probably in the future probably think about putting maybe a convection zone that begins sort of right there, say.
That's why I think the previous picture. Where is the alphatic magnet? Is that last one?
Okay, so yeah, so those red stripes, those are the alphatic transients there. So this is flux right here. This is a slice of magnetic flux, and you can see a very strong layer here. And you see these red stripes. This is actually over a short amount of time, so these don't move very much. But you can see between this one and, say, this one here, they've moved up a bit. In the density perturbations, you don't see them because they're not unstable. So there's still flux sitting up there that's being transported by these waves, but you know, the density perturbations are only being driven in a particularly strong, unstable layer.
And the time here is when you're in the same unit, says you quoted the next.
Yeah,
so they all
that's right.
Like 2.5.
That's right, yeah. So
That's the crossing time across the whole layer?
Across the thin layer, across the central layer. So that's right. So these things are breaking. These things aren't doing the best job of transport, and these alphatic transients do a way better job.
So the inertial time you find here, what is that?
That's okay. Yeah. So that's a shear turnover time of across this layer. So this is just basically the vertical derivative of the shear here. Yeah, diffusion time. So diffusion time is like this much, and this is a geometric average of the viscous and magnetic diffusion. So you know, it's like 45 and 70 or something like that, respectively. And so you know, this is a couple diffusion times basically, but these things are coming and going over a much shorter time scale than that. So whatever is causing these things to not remain coherent, they're not diffusing away. But yeah, alphatic time scales across this thickness roughly are about 2.5 units or even 0.1 units. And actually this 0.1 unit here is really sort of the kicker. This is what you should really be suspicious of right here. All right, so why do we think this is being inefficient? Well, the first reason I think is topology. If you want to have the vertical or radial shear inducing the magnetic gradient or magnetic structures in the way you want, like a layer, you have to have this magnetic field threading through vertically. There's nothing you can do about it, and so these things are fundamentally topologically connected to the bottom of the box. Now it's like ropes. If you want to move this thing up, you can get some slack here. And the rope that connects you to the top of the box, you can get some slack. But in the bottom, you're going to kind of stretch it out, and you're going to have this tension. So these structures, what happens is this, these field lines come in here down from below, and they wind through this domain a couple times. And then they eventually head up here. So one end of these tubes is tethered to this thing, and as they want to rise, they can't exactly rise all straight up at once. And to some point, one side is going to be a little bit more free to do so than the other. These things are going to tilt up, they're going to open up, where they attach onto the boundary and just kind of fall apart in some ways. And so you actually see this happening a little bit in the green movie as well. You see these structures kind of tilt and open up and then diffuse away. So that's one reason, perhaps. And then this is actually what you were getting to, I think. So another thing is these things expand, and they also, well, if you look, they're not particularly like idealized structures. These things have lots of holes. They're very leaky. Fluid can go in and out of these things like crazy. Lots of equilibration can happen. But you take a slice. This is in the longitudinal direction, depth, and then this is a slice at some latitude, if you like. You see this nice sort of. You see this strong central layer, really bright, but you see this nice sort of coherent, arching, tubular type structure. So this is a slice through a tube, and it's more or less all blue. It's all of one polarity. All right. Now, if you look at density, you see the nice strong central layer where there's low, and high density perturbations. But the structure is almost gone. It's there a little bit, but for the most part, it's much more present in magnetism than it is in density. And as these things basically rise up, they expand, they leak, and the density perturbations, which is driving the buoyancy forces, just sort of peters out. The magnetism is still there, but they just get up to some point and fizzle. All right, so there's one more thing about this, is that, so I mentioned that turnover time scale of 0.1, that inertial time scale of 0.1. That's a relatively strong shear time scale in this problem. And this thing forms a tremendous amount of turbulence. So this is a volume under entropy, same geometry here. This is shows this strong central layer of entropy here, which sort of dominates the vorticity in the whole thing. And then you see these other sort of structures, which I'll show in a minute. You can see them with vorticity lines. But there's sort of vorticity running around everywhere. There's a lot of turbulence in this. And these things are nifty. They're kind of just fun. They form these vorticity structures that are sort of these wound up structures. So you have this shear, which produces a lot of vorticity in the latitudinal direction. And so there's lines that have, they come in from one side and they tend to go out the other side of vertical lines. But they get wound up to this thing. And you can see one of these things sort of oscillating and then winding itself up. We think that the Crow instability, which is forms smoke rings out on trailing airplane wings. But it's a nifty thing. But basically, these things, the point is that you have a lot of vorticity that can just take magnetic field, wrap it up, chew it up, set it down to smaller scales, and then diffusion can take over from there. So, so you have a turbulent diffusion, if you like. So there's sort of these three things, equilibration, there's tethering or the topological issue, and there's a lot of vorticity running around this. It really doesn't help you a lot for transport.
You say that in the buoyancy patterns?
I'm sorry?
What is the buoyancy pattern?
I believe it's about 5. I mean, well, so I guess what do you mean about the buoyancy time? So if you look at one of these things that actually makes it all the way up, say, one of these events. So it starts off about 42, magic number, maybe to 48 or so. So the time of if one of these things was actually going to make it all the way up, it actually isn't too dissimilar from the Alfvénic time scale, if you like, because the slope of these things is relatively comparable, maybe a little faster. So now the thing is that actually that's an interesting issue, because if the buoyancy time scales were really fast, that means if the magnetic field was really strong and really wanted to rise a lot, then you might do better, you might say. If things just happen too quickly before anything else can take over. The issue there is that the strength of the magnetic field that you're creating is really intimately tied to the strength of the shear flow that you're forcing. And so now, let's see if I have time for a bit of a digression. Maybe, yeah. So I don't know if anybody's ever seen the show Mythbusters on Discovery Channel. It's a great show for any scientist. But what they do, there's some myth, and they want to test it. And it may not be false, but they want to test it. And they go and they test it, and they eventually oftentimes find that it is false. So there's an example of, can you fall into your washing machine and will it kill you on the spin cycle, spin you to death. And they take this washing machine on spin cycle, and they drop the dummy in there, and what happens, the thing just jams. And that's it. It stops. Okay, so they say, didn't work, myth busted. But they say, well, let's just figure out what we would have to have if we, in fact, wanted to be able to kill somebody with the washing machine. So they go get the Ferrari engine, and they hook it up to the washing machine, and they get this thing going like crazy. And then they get the dummy in there, and he spins around, and it would be certain death, right? So they say, okay, we've proven that it doesn't work, but let's find out what situation would have to have so that it does work. And actually, what I've been presenting to you this whole time is the Ferrari engine hooked up to the washing machine. It's not the actual case that you have in your home. This is actually what you have when you really want to figure out what extremes you have to go to get it to work. Because actually what I'm not telling you yet is that I actually tried this under much more reasonable circumstances, like you would have originally, and it didn't work. So what I'm doing here is just showing you that, okay, I can actually fudge it. But what do I have to do? Well, to fudge it, I actually had to force the shear flow extremely hard. Really, really hard. Much harder than I would have actually expected the Rachocline to need to be forced, in a way that I'll quantify in just a moment. But the idea is if you do this simulation without magnetism, you just say, let's see what this thing would do, if we forced it exactly the same, we'd just leave magnetism out. And you create this strong vortical layer. You have the strong layer of vorticity here, which is poking out at you. This is in the longitudinal direction, or latitudinal direction. So this is longitude here, depth. And so you create this strong layer of vorticity. And if you force it too hard, there is a stable background stratification, but if you force it too hard, it's going to overturn to Kelvin-Helmholtz instabilities. And that's what happens very rapidly. And the problem just becomes a complete mess. And you're generating all this turbulence because you're really forcing it extremely hard. And you see that this thing, it starts out sort of Kelvin-Helmholtz-like, and then it becomes fully 3D turbulence. And, yeah?
Sorry, I'm not sure I understand why you didn't work when you don't force it that hard. So what the structures you build are too large to become unstable?
Yeah. So actually, I'm next slide. So, yeah, we'll get there. But anyways, it's a pretty movie. I like it, at least. It's nice. Turbulence is pretty. But we had to force this thing so it would be severely hydrodynamically unstable without magnetism. And I maybe shouldn't even mention this, but like if this thing did not break apart through instabilities, if somehow by some magic this remained laminar, this flow would be, at least I'll say, ridiculously large for what we actually observe in the tachocline. It'd be, more than one order of magnitude larger. But the fact is that we also have estimates of the tachocline about their hydrodynamic stability to these types of instabilities, because you can measure this based on just stratification and shear gradients. And we know that we're well within the stable regime, or we should be well within the stable regime. This, of course, means there's limits to this resolution-wise and whatnot. But for the most part, either the tachocline looks like this locally, or something else is going on.
I thought we only have an upper limit on the width of the tachocline.
I'm sorry?
I thought there's only an upper limit on the width of the tachocline.
There is. So that's what I'm fudging that a little bit. You're right. So there is an upper limit. The thing is that right now we've got it down to about a thickness of about a pressure scale height. And if we made it tremendously thinner, it's, I don't know. I mean, how could it be, it would have to actually be sort of like a very small fraction of a scale height. Like a factor of 2 isn't going to get us there. So it would really have to be like 100 times thinner or something like that than we already think it is. And that just kind of starts to become a little bit uncomfortable. But,
so just to be clear, so you're saying that the amount of shear that you have at present in the simulations you were showing is comparable to having the tachocline be a tiny fraction of the pressure scale height?
That's sort of one way to sum it up. Now I'm showing this in this order, but chronologically, this is not how I worked this out. What I did was I computed a lot of 512 cube Alfvén waves that were one-dimensional. So if you take you start off and you look at the tachocline, and you sort of assume that model originally is sort of how it must work. Then you take something that's reasonable, with reasonable Mach number, reasonable stability profile, and you force this thing. And what you get is these are the same time depth maps of different quantities at this point, but and what they are is not tremendously important. But what you see is that there's no buoyancy rising events. These things you form this strong central layer, and this is enough time has gone by that you would have had an instability by this point.
You just increased the burn frequency from the previous one?
No, actually, in this particular calculation, all I did was I moved the layer deeper. These have the exact same stratification, same magnetic field strength, same forcing strength, and the layer is just a little bit deeper, and it becomes stable. So it actually turns out, I'm also cheating a little bit on this, but I've actually done a lot of calculations. It turns out that this Alfvén wave here, the reason I don't show it longer, I calculated the thing longer, this Alfvén wave comes down, it hits the bottom, it actually reflects back up, and when it reflects back up, it hits the central layer, gives it just enough magnetism, kicks it over the edge, and the thing becomes buoyant. But that's an unrealistic interaction with a lower boundary that you shouldn't expect. But the point is that this is sort of like really teetering on the edge of stability and instability. And what it means is that really ugly mess, or maybe pretty mess, but that mess was really, in some sense, close to marginal stability. This thing is really teetering on the edge, so that a tiny bump and you're going to get a drastic amount of behavior.
But as you wind up the magnetic field, do you keep on forcing the shear?
Yes.
So then you let it run long enough, the field would eventually get strong enough to pop out, no matter what the seed field were or the strength of the shear.
So that's actually, that's not exactly the way it is. So what you do is if you, okay, so there's a number of different ways of thinking about this. So the first way is if you don't, say, for instance, keep forcing the shear. In that case,
This is similar to the energy available and
Yeah.
balance that against the energy needed.
right.
to keep it sort of,
And so in this case, this is what I've got down here. If we begin with only a running shear and no shear maintenance, then we can only get magnetic buoyancy if extraordinary conditions are met. But those extraordinary
in the
conditions,
sun, you do have some
continual forcing.
forcing from convection.
Yeah, so if you do that, what you do is, so you have, in this case, you have just waves. You build up a layer sort of in a self-similar way that looks a lot like maybe the issue, the thing I showed on the beginning slide, but then eventually the thing begins to move up and down in this sort of self-similar way, in these wave dynamics, and the shear runs away from you and all that. Now, if you keep forcing it, then what you get is you get this stuff runs away, and you erode away sort of your profile and all that, and you get these sort of steady profiles that will eventually be there. But they won't continue to build forever. It becomes eventually a steady balance, where the forcing and the tension in the magnetic field are balanced. And how large this peak is depends on a number of things, but in particular depends on how strong the forcing is. And so if you want to make this peak bigger, you have to make the forcing bigger. Yeah.
There are two issues. First of all, the magnetic Hamilton scale is actually increased with the square root of the density contrast. If you move this deeper in, then I expect to be a stable or lower time scale. And secondly, there's magnetic field building up. This again actually sort of inhibits its ability to grow in the direction of your magnetic field lines.
Yes, so the magnetic field does quench the Kelvin-Helmholtz instabilities. Yes, it does. And I was just making that point to say that if there was no magnetism, but as you saw in the nonlinear calculation, there was quite a lot of turbulence going on there. There was quite a lot of overturning in that
Oh, I
case.
see. So the shear, there's zero velocity both in the top and bottom domains. So there's net zero velocity shift across the plane.
Yeah, well, that's what ends up happening if you try to. So if,
in the sun, for example, that would not be the case.
no, it's very hard to be able to balance tension with the type of forcing that would try to that in the absence of magnetism would try to maintain something like the tachocline. Now, we don't know a lot about sort of what the actual maintenance looks like. We know the end result of a very complex process. We don't know the beginning result, but it's very hard to I've thought about it a lot, and it's hard to figure out how you could get a steady balance of. In fact, it's impossible in these cases to get a steady balance of a localized field and a tachocline. Some net junction.
Sure, it will continue to wind up. That's why it was sort of asking to begin.
Yeah.
And then you have to pop out something.
Yeah. But these are the only kind of balances you can get. And so if you force the thing harder, then what you get, and then if you force it hard enough, you can get the instability to ensue before you get to this sort of balanced state. But you have to do that. So, okay, if extraordinary conditions are met, what do I mean by that? You can estimate what it would take for this thing to become buoyant. So you have some sort of a stability criteria, which is just sort of a ballpark, you say, okay? This quantity that relates to the magnetic field has to be, roughly the size of, maybe order of magnitude at least, of the Brunt-Väisälä frequency, the stable buoyancy frequency. Now, through a stretching process, and also through this case where you're continuously maintaining it, this still actually gives you, this quantity, this expression here gives you the best you're going to do with the shear. That you're going to build this thing up until the magnetic field is in roughly equal partition with the shear velocity. And it'll be in the shape of the derivative of the shear, so it'll be localized, and it'll have this rough magnitude. And at that point, either what you do is you'll end up adjusting to a state that is of this form with a different amplitude, or you'll end up just running away through waves. But this is really the best you can do as far as the gradients are concerned. So you can just plug these things into one another. Okay, that's sort of what you do. Is you plug them into one another and you rearrange some things, and you can get this expression where to get buoyancy, you must, at least ballpark-wise, expect that this quantity relating to the thickness of the shear and the pressure scale height must be at least on the ballpark of this Richardson number, which is the ratio of the buoyancy time scale to the turnover time scale. And for a very hydrodynamically stable flow, like we expect a tachocline is, this is a very large number. So, and this is all. The nice thing about this is this is all in terms of non-magnetic things. So we can try to estimate them from what we know without magnetism. And in the sun, the Richardson number in the tachocline is 10 to the 3 to 10 to the 5 or so. then the thickness is order 1, so this is way too big for this, and you're never going to really get there. You make the thickness smaller, you're going to change the Richardson number, make it smaller as well, but you're also going to make this thing smaller as well. So this thing gets smaller like the square of delta z, and this thing gets smaller like delta z, but still you're going to have to go a long way before you actually get there. So this is unsatisfied. If you actually this is not with continuous maintenance. If you continuously maintain it, you actually get a factor here of the eventual amplitude that has a magnetic Prandtl number sitting right out in front of this Richardson number, which in the sun is actually a small factor. So it turns out that the magnetic field can diffuse much faster than the viscosity, and you get this effect where actually the transients build up this magnitude here, but the eventual steady state ends up being actually smaller than this. So not satisfied. All right, and then the issues, should we have expected these issues? So there's actually quite a cottage industry out there to try to explain why the tachocline exists, independent of the dynamo. And they have all kinds of ideas about, the tachocline would want to burrow its way much deeper than it has over the time scale of the sun. And the question was, why hasn't it? And there's lots of ways of explaining this, but for the most part, there's one way is that you have some magnetism that is in the interior that's sort of bolstering this up. But regardless, these models really seem to require that you do not have field crossing the shear. If the field crosses the shear, then you end up with no tachocline. You end up with those kind of steady balances where there is no net jump and there may be some wiggly bits in the middle. But for the most part, you get something that's in magnetic isorotation. The gradients of the shear are perpendicular to the magnetic field. So,
well, is that reasonable? I mean, let me just go through this. I mean, if you have a 1-Gauss vertical field, let's suppose, then what you said is correct if the vertical Alfvén time with that field is shorter than the rotation period of the sun, right? Or the differential rotation period. And for 1 Gauss at a density of about 10 minus 2, basically, grams per cubic centimeter.
200 kilograms per cubic meter, so 0.2 grams per cubic centimeter.
0.2.
Yeah.
Okay. Then that makes it so easy. Then it's basically an Alfvén speed of 1 centimeter per second. And so over, say, 10 to 10 centimeters, that is a few hundred years, which is much longer than
a dynamo time scale.
So, so the point being that you have Reynolds stresses forcing differential rotation down into other parts of the tachocline, right?
Yeah.
Then in principle, you could maintain the tachocline with a vertical field that weak. It sounds like it's an order of magnitude because, right?
Well, that may be true. I mean,
because basically you erase radial differential rotation on
an Alfvénic time scale.
Alfvén time.
Right. But that's also the other issue, is that you also need to build a dynamo on that. The time scale of the dynamo has to be roughly the Alfvénic time scale of what it would take to stretch that stuff out. And so if you have an Alfvénic time scale that's too weak, I guess the issue is that you want that field strength to be sufficient to be able to generate a field on a dynamo time scale, and you also want it to be sufficiently weak so that it doesn't screw everything up. And it just seems like those two things are sort of in contradiction to one another, at least in a ballpark sort of way. I'm kind of doing a little short on time. I mean, I don't know, we started a little...
Well, if you get lots of questions during the talk, then, certainly another 5 minutes is no problem whatsoever.
Okay. So, I'll do this and I'll just try to wrap it up then, yeah. So there's one other issue, is that you get this effect of buoyancy trying to push stuff up. And this is an issue of terms in the momentum equations generating a flow that then goes back into the induction equation and hopefully transport field. There's this other effect called magnetic pumping, which is the effect of a background flow, which actually just directly transports magnetic field, but it does it in the downward direction. So there's this issue with the fact that you have these small plumes in a compressible environment that have a major up-down asymmetry, and they tend to transport a mean magnetic field. So this is a calculation done by Nick Brummel, actually, where he just took a very strong slab of field, in a convection zone. So this is an unstable part, and there's a stable region below. And this is like that a la Catania and Hughes. This is a discontinuous slab, essentially. And this has got a plasma beta of essentially 1. So this is a very strong field. and it's in a convection zone. And what you'll see when I play the movie here is that this thing has a tendency to initially want to rise. It does want to break apart and rise. But you'll see what ends up happening in the end is the convection will win. And you start off with a region here, sort of imagine sort of halfway along that line there. And you'll see where the stuff ends up eventually is farther down. So there is this magnetic pumping effect that is quite robust. And you can see now, and then it jumped back up at the end. So we'll play that one more time. So this thing wants to tend to transport magnetic field down. And it turns out that a magnetic structure that's trying to rise through a turbulent convection zone, which I had not modeled, actually needs to be basically the average energy in that structure needs to actually be greater than the peak energy in the convection. Because it's sort of like it only takes one bullet to sort of kill one of these things. That it only takes one plume to come down through, break this thing apart, tear it open, and it's gone. So this magnetic pumping mechanism is quite robust. So I'll sort of summarize this later, but if you have convection maintaining this stuff, then you're not going to expect the shear to be tremendously stronger than the Reynolds stresses that are doing that. And then you're not going to expect the magnetic field to be tremendously stronger than the shear. So you're not going to expect the magnetic field to be tremendously stronger than the plumes. But then they've got to beat the plumes in the end, because if they don't, they're going to get torn apart. So there is this sort of other problem. And then to sort of relate this to other stars, there is this issue that if you look at low-mass stars, the really low-mass stars that are fully convective and expected probably do not have any sort of Rachocline. There's a lot of them that are active. So this is the fraction of them that are active, and then there's a lot less of them that are active here. But the point of this is there's a lot of ways to interpret this, and Matt here knows a lot more about this than I do, for instance. But the point is that there are stars that probably do not have tachoclines that still have activity. So it isn't a requirement, in a sense. Okay, so summary. Shear generated magnetic buoyancy is possible. Right? We did it. You got to hook it up to the Ferrari engine to do it, though. You have to force it unrealistically hard. And even then, and probably because of that, you've had to hook it up to the Ferrari engine, it's ineffective at transport. There's steady global models. Okay, this is sort of heuristic, but there's steady global models that do not want field crossing the tachocline, or else you end up with isorotation on an alphanic timescale. The magnetic pumping is known to be very robust, and that stars without a tachocline have activity also. So then conclusions. All right, so this is to sort of summarize it. If the shear is constrained by the stable stratification, and the magnetic field is constrained by the shear, then how can the magnetic field overcome stable stratification? I don't know, maybe it can, but I don't know how. Then another conundrum is if the shear is generated by convective plumes, how could shear-generated magnetic fields then overcome those same plumes and avoid pumping? So that's another problem. And this is another key issue. We don't see, if this is all about alphanic processes and stretching and these kind of things, and we're hoping to get these things in equipartition with the shear to get these things buoyant or whatever, we don't see a helioseismic response in the tachocline. We see a helioseismic response in the dynamo scale near the surface, but we don't see it in the deep down. There's about maybe a 1.3 year signature down deep, but that's even still fuzzy. So, and we don't have any idea what that could be. So the tachocline is interesting, but perhaps it is not quite as useful as once thought for the dynamo. And this is a good stopping point. I have more stuff that I can discuss with anybody who's interested later on about sort of future ideas and where to go from here. So I was going to cover some of this, but it turns out we can leave that for later. And that's about it.
Given the time, maybe let's move most questions to the discussion, most discussion to the cookies, but is there any urgent questions that people want to ask?
Yeah.
All right, then let's talk over cookies.
Sure. Thank you.